So we are on page 11 of the notes, the chi-squares distribution. We have discussed some of all these properties and the distribution itself before now, and this is just the note to clarify certain things and to document what we have been discussing without the note before now. So it's a continuous probability distribution with only one parameter, that is the degree of freedom. That is the only parameter of the chi-square distribution, and it is it has only one parameter, the degree of freedom, and that degree of freedom defines the distribution. The mean, the variance, and several other properties of the chi-square distribution are related to the degrees of freedom of the distribution. So the PDF has been given. Just take note of that, as well as all those properties, that the mean is equal to the degree of freedom, the variance is 2 times the degrees of freedom, the median has been given, the mode has also been given, and so on, as well as all those other properties that are stated there. So that is for the chi-square distribution. From the explanatory notes, we can see that um, the skewness is given by 8 over root k, 8 over k, the square root of everything, 8 over k. That is the skewness. It also has SS kurtosis, 12 over k. The median, it has an approximate value of it, given by k into bracket 1 minus 2 over 9k, all raised to power 3. That is an approximate value of the median. The chi-square distribution is a skewed distribution, as we all know. Unlike the normal distribution, it is skewed, and the skewness parameter is given by square root of 8 over k. So skewness is talking about the degree of the skewness and kurtosis. They are related to the peakedness, the peak, and the nature of the tails, whether the tails are heavy or not, and whether the distribution is having a peak, unlike a normal distribution, which is symmetric. The chi-square distribution is not symmetric. It is skewed to the right. The moment generating function has also been given. The moment generating function of the chi-square distribution is 1 minus 2t, all raised to power minus k over 2, where k is the degrees of freedom of the chi-square distribution. And it's also there that the chi-square distribution with parameter k, or k degrees of freedom, is really the sum of k independent normal random variables, standard normal random variables that are independent. It is the sum of them, the square of it. That is, if Z1, Z2 up to Zk, I'm reading from the note now, as it's also there in the explanatory note, that if you have k independent standard normal random variables, and you square those random variables, then the sum of all those variables will give you a chi-square distribution with k degrees of freedom. The chi-square distribution also has the important property of additivity. What this means is that if you have two or more chi-square distributions and you add them, independent chi-square distributions, let us take note of that. Two or more independent chi-square distributions, and you add them, their sum will also be chi-square. The sum of any number of independent chi-square random variables is also a chi-square distribution. It is an important property of the chi-square in that the sum of any chi-square will also be chi-square. Not all probability distributions have this property, this additive property. The sum of two exponential random variables is not exponential. It is rather a gamma distribution or an Erlang, as the case may be. Properly put, is an Erlang distribution. The sum of two normal random variables, is it a normal distribution or not? You can put your comment on the chat. The sum of two normal random variables or two or more, is it normal? Yes, yes. The sum of two normal random variables, is it normal or is not normal? Yes, the sum of two normal random, independent random variables is also normal. So the normal distribution also has that additive property, but not all distributions have that property. The chi-square is just one of them that is privileged to enjoy that additive property, which makes it possible for them to be added together, and you will still have a chi-square distribution. Now, that additive property can be proved easily using the moment generating function. The moment generating function. And I think we have done that in the explanatory note that you can find. If you have not gotten it, you can get it later. So if x1, x2, xn are independent chi-square random variables with k1, k2 up to kn degrees of freedom respectively, then if you have another random variable y, which is equal to x1 plus x2 plus up to xn, is also chi-square distributed with degrees of freedom equal to the sum of all the individual degrees of freedom. That is k1 plus k2 plus k3 up to kn. That is a chi-square distribution. We can use the moment generating function. We have the moment generating function of the chi-square to be 1 minus 2t raised to power minus k over 2. When you now use that for the random variable y, you have myt is equal to 1 minus 2t to power minus, let us say, let us call the degree of freedom of the random variable y to be, we don't know it, let us call it k star, k asterisk. So if that is k star, you will now input the values, I mean, y is equal to x1 plus x2 plus x up to xn. You incorporate it into the MGF so that myt will now be equal to m subscript s1 plus x2 up to xn of t. Now the sum of n independent and independent random variables, their moment generating function, the sum of their moment generating function, it's telling, I mean, the moment generating function of the sum, let us put it correctly, the moment generating function of the sum of n independent random variables that are x1, x2 up to xn, the MGF of the sum is equal to the product of their individual MGF. Those are properties that we have talked about for the moment generating function in the earlier classes. So we are going to make use of that to obtain the MGF of y. So when you have that multiplication there, you multiply individual MGFs together. That is mx1 of t times ms2 of t up to mxn of t. You multiply all of them together. When that is done, and you now incorporate the formula for the mxt, which is 1 minus 2t to power minus ki over 2 for each of them, it will resolve when you do all the necessary computation and rearrangement. You will now have the MGF to be equal to 1 minus 2t to power minus half into bracket 1 minus half into bracket k1 plus k2 plus k3 plus k4 up to plus kn. That is the sum of all the individual degrees of freedom, k1, k2, k3 up to kn. So when you now resolve that, you will now see that actually k1 plus k2 plus kn is equal to, we have called it k star. So the MGF of that distribution that we have obtained is, and we have said that the MGF is uniquely defined for any distribution. The MGF of a chi-square distribution is different from the MGF of a normal distribution. So when you see any MGF in the form of a chi-square distribution, you know that it is a unique representation of the chi-square distribution. You can now make inference and conclude that that distribution is chi-squared, then with the particular parameter, which is the degrees of freedom. In this case, the degrees of freedom is k1 plus k2 plus k3 up to kn, which we have now defined as k asterisk. So that would be the degrees of freedom of the new chi-square distribution defined by y. So y is distributed chi-square with k star, k asterisk degrees of freedom, where k asterisk is equal to k plus 1, I mean k1 plus k2 plus k3 up to plus kn. That will be the degrees of freedom of the of the new variable, which is the sum of independent chi-square random variables with different degrees of freedom. I hope this is clear enough. Any question before we proceed further? Any question? Yes. Make your comments on the chat. I should explain again the additivity property. Is in summary, what it's saying is that the sum of any number of independent chi-square random variables is equal or is distributed as is also a chi-square distribution with degrees of freedom equal to the sum of the individual degree of freedom of those random variables. For example, if you have chi-square 5 and chi-square 7, two chi-square distributions. One of them has 5 degrees of freedom, the other one has 7 degrees of freedom. We are saying that if you define y is equal to x1 plus x2, where x1 is the one with is the chi-square with 5 degrees of freedom, and x2 is the chi-square with 7 degrees of freedom, then y equal to x1 plus x2 will also be distributed as chi-square with degrees of freedom equal to the first degree of freedom plus the second degree of freedom. That is equal to what? What will be the new degrees of freedom of y if y is equal to x1 plus x2? 12. So it is 5 plus 12. Essentially, that is what we are saying. It will be 5 plus 7, which is 12. And if you have 3, 5, 7, and 4, it will be 5 plus 7 plus 4, 16, and so on and so forth. The only principle to take note of is that they must be independent. Because if they are not independent, those computations will not be possible. Those computations will not be possible, and the assumption is only valid when they are all independent. So essentially, that is what the additive property is saying. That the sum of any number of chi-square random variables will always be a chi-square distribution. Unlike some other distributions where the sum of two of those random variables, even though they are independent, is not necessarily that distribution. So that's the additive property of the chi-square, and it makes computation using chi-square distribution to be straightforward. Now, the chi-square distribution really is used to test for variance, and that's one of the tests available for chi-square distribution. To test a variance, whether it is significantly different from an hypothesized value. For example, the population variance is known to be 5, e.g. 5. You now obtain your data and estimate that variance, and you found that is a certain value, maybe 12, from the data itself. You cannot test the hypothesis H0 that the population variance is equal to 5 against the alternative hypothesis H1 that the population variance is greater than 5 or less than 5, as the case may be. So it is the chi-square distribution that you will use to test that kind of hypothesis. When you are testing hypothesis about single variance, comparing single variance with the population variance, the chi-square distribution is the appropriate, or the chi-square test is the appropriate one to use. Of course, the chi-square distribution has several other tests that it can be deployed to. The chi-square test of independence, chi-square goodness of fit test, and several other ones. It is a very, very useful probability distribution. And again, as we will see later on, the ratio of two chi-square random variables that are scaled with their respective degrees of freedom, their ratio is distributed as an F distribution. An F distribution, which is the next probability distribution that we'll go into. So, together with what is on the note, these few things should help us in understanding more of the chi-square distribution. Now, I have a number of exercises. I have a number of exercises on the explanatory notes. And the first question there is that you should use the moment generating function of the chi-square distribution to obtain the first three moments, the first three raw moments, that is expected value of x, expected value of x squared, and expected value of s cubed. Then you can now use your results to obtain the variance and skewness of the distribution. The variance and skewness of the distribution. I hope we have gotten the notes now. Both notes. Have we gotten that? Have we gotten the notes? So you can see the question on the notes. It's in the second page that you should use the MGF to obtain the first three raw moments and use that to determine the variance and skewness. So we have not given a formula for the skewness. So I expect you to search and get a formula for skewness, which you will now use on the basis of the data you have, what you have computed for the moment. You can now use that formula to obtain the skewness of the chi-square distribution. The skewness of the chi-square distribution. So that is that's the first question. That's the first question. The second question is, if you have k independent and identically distributed chi-square random variables with p degrees of freedom, what will be the distribution of y, which is the sum of all those k independent and identically distributed random variables? What will be the distribution of that? So I expect you to work on those questions. For the first question, let me give you an hint on how to go about it. You will use the MGF 1 minus 2t to power minus k over 2. Use it by differentiating it the first time and evaluating at t is equal to 0. You will obtain the mean, which is equal to k. You differentiate it the second time and evaluate at t is equal to 0. you obtain the expected value of x squared. You also differentiate the third time and evaluate at t is equal to 0 to obtain the value of expected value of x cubed. Now, the variance is just expected value of x minus expected value of expected value into bracket x minus expected value of x, then you close the bracket and square everything. That will be the variance, and it's also equal to expected value of x squared minus expected value of x all squared. That is, the variance is equal to the second raw moment minus the square of the mean, or the first raw moment, minus the square of the first raw moment. You use that to obtain the variance. The skewness, there is a formula for the skewness, which you can now expand it to get the relationship that you will now plug in all the values of expected value of x, expected value of x squared, expected value of s cubed into the formula to obtain the value for the skewness. That is that for that question. The second question is similar to what we have done, what has been done for the sum of n independent chi-square random variables with k1, k2, up to kn degrees of freedom. They have separate degrees of freedom, but this time around, we are talking of, it's not separate degree of freedom as it were. So it's the same principle with minimal readjustment to fit the question. So the third question is saying that if you have a chi-square distribution with 2 degrees of freedom, you should obtain the mean, the median, the mode, the MGF, the skewness, and the SS kurtosis. I think this one can warrant us, let us do it right away. The first question, if S is chi-square distributed with 2 degrees of freedom, the mean is equal to what? The mean, put your value for the mean here. The mean will be equal to what? Yes. Chi-square with 2 degrees of freedom has a mean of what? Nobody. It has a mean of 2, that's correct. It has a mean of 2. The median will be equal to what? The median will be equal to what? Put it in the comment. What will be the value for the median? So the median will be 8/9 raised to power 3. What value is that? 8/9 raised to power 3. 8 over 9 to power 3 is equal to what? That will be the value of the median. 0.702. That will be the value of the median. The next one is the mode. What will be the value of the mode? The third item there is the mode.
The set is ready. Okay, you are preparing your class.
I'm in the class.
Okay.
So what will be the value of the mode? Mode. Somebody has said 0. The mode is 0. Is that correct? Why is it 0 if that is the case? So the median is 0.702. Please take note. 0.702. Somebody says 0.704. 0.702 is the median. The mean is equal to 2. The variance, the mode is equal to what? The mode is equal to why is it 0? Okay, it's correct. The mode is equal to 0 because the formula for the mode is the maximum between k minus 2 and 0. So k minus 2 is 0, the other one is 0, so that value is equal to 0. That will be the value of the mode. What will be the moment generating function of that chi-square distribution with 2 degrees of freedom? What will be the formula for the MGF? It will be 1 minus 2t raised to power minus k in this case is equal to 2. So 2 over 2 is 1. So 1 minus 2t raised to power minus 1 will be the value of the MGF of that distribution. Chi-square with 2 degrees of freedom is MGF is equal to 1 minus 2t to power minus 1. That is 1 all over 1 minus 2t. That is the MGF of the chi-square with 2 degrees of freedom. What is the value of the skewness? The skewness of that chi-square distribution. The skewness is 8 over k, the square root of 8 over k. So 8 over 2 is equal to 4. So the square root of 4 is equal to 2. So it has a skewness of 2 exactly. I'm coming. Okay, thank you for reminding me. Yes, there's an error. There's an error in the value of the median. We didn't multiply by 2. So when you multiply by 2, it will now be 1.4. Thank you. So the median will be 2 times 0.702. That is the value of the median. 2 times 0.702. Which will now give us 1.404. So thank you for pointing out that error. So that is the value, that's the formula for the median, and the correct value is 1.4. So you can see that the mean is 2, the median is 1.4, the mode is we found out to be 0. So you can see that the mean of the distribution is higher than the median, telling us that the distribution is skewed to the right. Skewed to the right. So once the mean is bigger than the median and the mode, the bulk of the distribution is to the other side. So that is the essence of it, and that is the essence why we say it's a skewed distribution. So the next question is the skewness. And what's the value of the skewness of that distribution? Chi-square with 2 degrees of freedom. Okay, we have gotten that to be 2. We have gotten that to be 2 already. The next question there is the SS kurtosis. SS kurtosis, which is just 12 over k. 12 over 2 is equal to 6. That's the SS kurtosis. Then f of x itself, the distribution itself, the PDF. You just go to the PDF formula and put wherever you see k, you put 2 there, because we are talking about 2 degrees of freedom. So wherever you see k, you incorporate 2, and that will simplify it a bit more, so that you will now have it will simplify it further in such a way that you now have the denominator. The denominator, that 2 to power k over 2 will just be ordinary 2, because k is equal to 2. So k over 2 is equal to 1. So you have 2 raised to power 1, which is just ordinary 2. Then the k over 2 gamma function, gamma k over 2, which we have there also in the denominator, is just 2 over 2 gamma 1. So and that is equal to 1. So all those other things, we just have 1 over 2, then x to power k over 2, which will now be equal to x to power 1 itself. K over 2 minus 1, that is the x will become absent, and you have e to power x over 2. E to power x over 2. So that will be the PDF of the chi-square with 2 degrees of freedom. That will be its own PDF. So you can You can see that the questions, they are straightforward. You can repeat that for the other things. That is, you do it for chi-square with 10 degrees of freedom, chi-square with 12 degrees of freedom, chi-square with 6 degrees of freedom, and chi-square with 4 degrees of freedom, respectively. So that will not give us any problem. They are straightforward. We will now proceed to the F distribution. The F distribution. Yes, sir. The F distribution, as I said before now, it arises as a random variable that is a combination of two scaled chi-square distributions, independent, scaled, and it has, for the chi-square distribution, we have only one degree of freedom, one parameter. But the F distribution, which is a combination of two chi-square distribution, the ratio of two chi-square distribution, it has two parameters. The degree of freedom for the numerator, represented by D1, and the degrees of freedom for the denominator, represented by D2. So the two parameters of the F distribution are the degree of freedom for numerator and degree of freedom for denominator. Those are the two parameters of the F distribution. And we have given, in the explanatory note, we have provided the f of x of the F distribution. It's a bit complicated, but that is how it is. Just for your attention, take note of it. The placement of the degrees of freedom, D1 and D2. Now, for the chi-squared, for the F distribution, there is a convention, a rule that, because the distribution is always greater than zero, it ranges above zero upwards. So the degree of freedom that has the highest value is taken as D1. For example, if you are comparing two chi-square distributions, one of them is chi-square 6 and the other one is chi-square 10, and you want to find a ratio of them, the one that has the highest degree of freedom is taken to be the first random variable. That is, D1 will be equal to 10 and D2 will now be equal to 6. So the numerator degree of freedom is always, as a rule, taken as the larger one, so that you will have values of the random variable that are essentially bigger or greater than zero. And you can now use it to test hypothesis. Now, as I said before now, the chi-square distribution is used to test for a single variance, whether it is different from an hypothesized value, population value. By extension, the F distribution can be used to test two variances from samples, whether they are different from themselves, whether they differ significantly between themselves. That's the essence of the F distribution, and we make use of it in several instances: the analysis of variance, in testing parameters of regression, significance of the parameters of the regression model, and several other ways where you make use of the F distribution. It has a few properties which we have stated in the notes, in the main note. The mean is given by D2 all over D2 minus 2, with the assumption that D2 is, that is the degree of freedom of the denominator, the smaller degree of freedom, will always be bigger than 2. It's always greater than 2. The variance is also given there with the assumption that D2 is always greater than 6. And a number of other properties. The mode is equal to, that is, you can find this, the mode, the formula for the mode, you can find it on the explanatory notes. It's there. The mode is D1 minus 2 over D1 multiplied by D2 all over D2 plus 2. The skewness formula is also given with the assumption that D2 is greater than 6. It must be bigger than 6. If not, you are not able to compute the skewness for the F distribution. Then the moments can also be obtained. The kth moment can be obtained by that formula in property 5 stated in the explanatory notes, that it is equal to D2 over D1 all raised to power k multiplied by gamma of D1 over 2 plus k times gamma of D2 over 2 minus k all over gamma of D1 over 2 times gamma of D2 over 2. Now, to obtain this moment, let me explain it more for us to understand it better. If you want to obtain the first moment, that is k is equal to 1 in that formula. K is equal to 1 in the formula stated in property 5 in the explanatory notes. That is, you will now say D2 over D1 to power k, k is equal to 1, so D2 over D1 to power 1, it remains there. Then gamma D1 over 2 plus k. Now, D1 over 2 plus k, we want to find the gamma relationship, gamma of it. We know that for integer values of the gamma function, it can be resolved into a factorial relationship. You can put it in terms of a factorial, so that gamma, if k is an integer, this is a question for us now, and I want us to answer it. If k is an integer, a positive integer, then gamma k is equal to what in terms of factorial? Express gamma k in terms of factorial if k is a positive integer. You can put your answer straight away so that we proceed with it. Anybody yet? Nobody? Somebody say k minus 1 factorial. That's not correct. Yes, it's correct. Sorry. No, no, no. If k is an integer. Okay. Yes, it's correct. Sorry. It's correct. It will be k minus 1 factorial. K minus 1 factorial. So it can also be expressed as a recursive gamma function, in that gamma k is equal to k minus 1 times gamma k minus 1, and so on and so forth. So if you have that in that property 5, you can easily so for example, if D1 is equal to 4, for example, then the numerator D1 over 2 plus k will be equal to what? When k is equal to 1 now, we are talking about the first raw moment. You will now have 4/2 plus 1, which is 2 plus 1 equal to 3. Gamma 3 is equal to what? 2 factorial. 3 minus 1 is 2. So then 2 factorial is equal to 2. So that will be gamma 2. Then if D2 is also, for example, 2, it cannot be 2 in the real sense because 1 minus k will now be 1 minus 1, 0. So it will not happen. For example, if D2 is 4, it will now be 4/2, that is 2, minus 1, 1. Gamma 1 is equal to what? Gamma 1 is equal to what value? Yes, put it in the comment quickly. Yes, gamma 1 is equal to 0 factorial, which is equal to 1. So gamma 1 is 0 factorial and is equal to 1. So you can only have gamma 1 upwards. From gamma 1 upwards, gamma 2, gamma 3, gamma 4, and so on and so forth. So the advantage of those F distribution that has even values for their degrees of freedom, you can easily manipulate the value to get the moment easily using the formula in the moment generating formula in property 5 in the explanatory note. Let us go back to the main note itself. There are other properties that are listed there for the F distribution, that the values of F cannot take negative, it cannot be negative, because being that it's a ratio of two variances, variances can never take negative value. So the value of F will never be negative. The distribution is positively skewed. It is a positively skewed distribution. Also, the mean is approximately equal to 1. The mean of the F distribution is approximately equal to 1. Then, the fourth property is saying that the F distribution is a family of distribution of curves that are based on the concept of degrees of freedom of the variance of the numerator and the degree of freedom of the variance of the denominator. That is what is conceptualized by the F distribution. Now, any random variable that is distributed as F with D1 and D2 degrees of freedom, as I said, it arises as the ratio of two scaled independent chi-square random variables. Take note of the words scaled and independent. Those are critical part of it, because you scale it, you scale the chi-square random variable by dividing it with its degrees of freedom for both the numerator and the denominator. And the assumption is that both of them are independent. If independence cannot be established, then you cannot proceed any further and you cannot make any inference or postulation about the distribution itself. And it's the distribution can also be obtained, but it is what we are dealing with, the distribution we are dealing with is the central F distribution. There is also the non-central F distribution, which has some of all those properties as the F distribution, but it has a non-centrality parameter. It has a non-centrality parameter. So that is that for the F distribution. And if x if if u1 is distributed as chi-square with d1 degree of freedom and u2 is distributed as chi-square with d2 degree of freedom, then the ratio u1 over d1 all over u2 over d2 is distributed as an F distribution with d1 and d2 degrees of freedom, and with d1 always greater than d2. d1 is always greater than d2. So that is part of it. Those are the properties of the F distribution. Now, there is an exercise there that given that U1 is distributed as chi-square with 8 degrees of freedom, and U2 is distributed as chi-square with 6 degrees of freedom, and they are both independent chi-square random variables, and x is equal to U1 over D1 all over U2 over D2. We are told to obtain the following parameters for the distribution, the following statistics: the mean, the variance, the mode, the skewness, and the second moment, the expected value of x squared. So how do we do that? I can explain it, even though it is straightforward. It's essentially asking you to compute the mean, the variance, the mode, the skewness, and the expected value of x squared for a chi-square, rather for an F distribution with 8 and 6 degrees of freedom respectively. So let us proceed for straight away. Expected value of x will now be equal to what? Expected value of x is equal to 8, rather 6 minus 6, 6 all over 6 minus 2. That is 6 over 4, or 3 over 2. 3 over 2, that is the value of the mean. Of course, D2 is always greater than 2, and it is satisfied in this case. The variance. What will be the value of the variance? You just plug in those values there and get your answer. If you are able to get it as we proceed, you can notify me. The mode is D1 minus 2 all over D1 multiplied by D2 over D2 plus 2. So D1 minus 2 all over D1 is 8 minus 2 over 8. That is 6 over 8. Then D2 over D2 plus 2 is 6 over 8. 6 over 8 times 6 over 8. We can easily cancel out and reduce the fraction to be what? Excuse me. Nine over 16, correct. So 9 over 16 will be the mode. We should take note that the variance will be around 1, really. When we do the computation, the variance will be around in the neighborhood of 1. We can also compute the skewness using the formula that has been given there also. And the moment, the second moment, that is expected value of x squared, is just for you to incorporate expected value of x, excuse me, k will be equal to 2. K will be equal to 2, and you now do the computation using the moments formula. So that is that for the F distribution. Any question? Excuse me. Questions? Quickly, any question? F of S of the chi-square distribution. It is there. Look at the notes. Look at the main note itself. We have stated it there. F of S of chi-square distribution is there, and it is straightforward. It is straightforward. 1/2 raised to power k over 2 multiplied by gamma k over 2. Then now multiplied by x to power k over 2 minus 1. Then exponent of minus x over 2. X is always greater than 0, and k is also always greater than 0. That is the PDF of the chi-square distribution. So if you are to compute the PDF of chi-square 2 distribution, you just, anywhere you see k in that formula, you incorporate 2, you replace it by 2 or any other value as the case may be. If you are doing for chi-square 8, anywhere you see k, you replace by, you substitute 8 into it and resolve the fraction into a simple form. That is the formula, that is the way to go about it. So that's how to, that's the PDF of the chi-square distribution. More questions, please. In the exercise, k is not equal to 2. The F distribution exercise, there's, okay, k is equal to 2. The k we are talking about is not degrees of freedom. The moments, property 5 in the explanatory note, it gives us a formula mu x of k. The k is the power or the particular moment you are interested in. If it's the first moment, k is equal to 1. If it's the second moment, k is equal to 2. So k is equal to 2 in the case of this exercise because we are talking of the second moment, the exponential value of x squared. That is why k is equal to 2. If you are talking of exponential value of x cubed, then k will be equal to 3, and you substitute it into that formula together with the D1 and D2 and resolve it. That is the use of the k. It varies from 1 to any number, depending on the moment you are interested in computing. That is the use of the k. Any other question, please? We have explained what that function on the numerator represent? It is the gamma function. Go to the gamma distribution and see where we explained it. It's clear there. It's clear that you are not going through your notes. It has been defined when we are talking about gamma distribution. It is called the gamma function. And it's an integral combining the exponents and x to a certain power. So it is the gamma function. Go to the note on gamma distribution. You will see what it means and how it has been defined. And we have said also that when we are talking about integers, when the component of that function are integers, then the gamma function resolves into a factorial, so that gamma k will now be equal to k minus 1 factorial, which we also ask even in this some moments ago. So that function is a gamma function in the formula. It is the gamma function. Go to the note on gamma distribution and you see it there. Any more question? Any more question? Can we proceed? Okay, poor network. Sorry for that. I was asking whether there is any additional question or we can go ahead now. Okay, so let us look at the last item on the present note. The distribution, other statistics is on page 13. It's on page 13 of the lecture notes. So the other statistics are very important statistics that are used mainly in non-parametric inference or non-parametric statistics. It is defined. The kth order statistic of a random sample or a sample containing n observations is just the kth smallest value. So other statistics essentially, as the name specifies, when you have a sample and you rearrange them by way of their values or the realizations of that random variable, which is the value, the observation that you have obtained, you arrange them in increasing order. So if you have a sample of size n, you sort it and rearrange in increasing order. So the position of each value, starting from 1, 2, 3, 4, 5. Those are the other statistics of the random variable. So if you have rearranged it, The first variable is called the minimum. The last variable of the other statistics is called the maximum. The middle value, when you have an odd numbered sample, is called the median. And you can have several other statistics from that. You can have the range. The range, what is the range? What is the range? It's just the difference between the maximum value and the minimum value. The maximum minus the minimum gives you the range, and it is a measure of the dispersion or spread of the sample. The wider the range, the greater the dispersion, and the smaller the range, the less you have dispersion in it. So, and several other statistics that can be gotten, the quartile, the interquartile range, the quartiles, and so on. You can obtain them using the other statistics. Important cases of other statistics are the minimum, the maximum, as I said, the median, and the quantiles, the sample quantiles. So when we are analyzing other statistics from a sample, a random sample, and that is assumed to come from a continuous probability distribution, we are able to compute the cumulative distribution function based on that sample. And using that, it is possible to significantly reduce the computation that you will do by making use of the CDF, which the range of the CDF, what is the range of values that the CDF can take between what and what? The cumulative distribution function of any random variable can take values between what and what. The CDF of a random variable takes values between what and what. It takes values between 0 and 1, really. The smallest value is 0 and the largest value is 1. That is the nature of the CDF. So you can use that to simplify your discussions and argument and analysis, making use of other statistics from the uniform distribution between 0 and 1. Now, if you are given a random sample x1, x2 up to xn, the way to go about it, as I said, is to sort, if you want to compute other statistics, is to sort the sample in increasing order and rearrange the values according to their size. Now, you can write this one down if you can hear me well. Take these 5 values. 20, x1 is equal to 20, x2 is equal to 10, x3 is equal to 4, and x3 is equal to 4, x4 is equal to 5, and x6 is equal to 2. x6 is equal to 2. Now rearrange the data in increasing order. Rearrange it in increasing order. So you can easily rearrange from the smallest 2. X1 will now be equal to 2. And the convention, how to write the other statistics is different from what we have in the normal random sample. Instead of writing x1, x2, x up to xn, you will now write it inside the the subscripts will now be inside a bracket so that x1, the first order statistics will be represented by s into bracket 1 in the subscript, s subscript bracket 1, which is the minimum, and the maximum will be x subscript into bracket n, which is the largest value, and so on. So you use the brackets within the subscripts to differentiate between the order statistics and the random sample itself. Of course, we know that if you have a random sample of size n, x1, which is the first observation, may not necessarily be the smallest value. Likewise, xn, which is the last observation, does not necessarily imply that it is the largest value. So it is when you have ordered them appropriately, that is when you can now talk of the other statistics. You can now talk of the other statistics. So it's just essentially you sort them and rearrange them from the smallest to the largest so that x bracket subscript 1 is less than s of 2, less than s of 3, up to less than x of n. Essentially, that is what is done in obtaining the other statistics from the data, from the sample that you have gotten. You rearrange the data, you sort it according to increasing values. The smallest is the minimum, the largest is the maximum. So if you have a set of random variables, capital X1, X2 up to Xn, that is, random variables are represented by capital letters, while samples are represented by small letters. So sample observations are represented by small s1, small s2, and so on. While random variables, group of random variables are represented by capital X1, capital X2, and so on. So that is the convention in representing random variables and samples, random samples. So if you have a set of random variables, capital X1, X2 up to Xn, then you can also apply that principle of ordering. You can have the order statistics of the group of random variables x1, x2, xn by ordering their various realizations. Any observation that comes from a random variable is called the realization of that random variable. So you can rearrange them and will now be able to have functions that will obtain the distribution of the kth order statistics, which has been given in the notes, and also the cumulative distribution of the minimum and the maximum has also been given. So I think the explanatory note that I will provide for this one will explain it further, and we'll look at a few examples to clarify the issue and make it to be clearer. This note is just for your perusal. I will also provide the explanatory notes in a few examples and exercises on that for other statistics so as to make it to be a bit more clearer for us. I think this is a good time to conclude the class. Before I go, any other question again? Any other question? Quickly put it on the chat. I will see it straight away and respond. Any question? Okay. So what about chi-square? Just take your time to, how do you get the expected value for chi-square? You can get it directly by doing the expectation from the PDF. Expected value of x is equal to x times the PDF f of x dx. You integrate over the range. You integrate over the range of values. You can also obtain the mean by differentiating the moment generating function once and evaluating it at t is equal to 0. You also obtain the mean like that. So those are a number of ways that you can use to obtain the mean of the chi-square distribution, as well as any other moment, really. Indeed, the expected value of x squared can also be obtained through the same method, expected value of s cubed, and so on and so forth. You use the PDF or you use the moment generating function to obtain the mean. So thank you very much and have a nice day.